Hello, I'm Leandro Silva from the University of Pernambuco and Federal Institute of Paraíba, and I'm going to do the short presentation of the paper Binary and Multilabel Defect Classification of Printed Circuit Boards based on Transfer Learning. At first, we are going to talk about motivation, then we are going to discuss the proposed approach, following the methods, and finally, results and conclusions. Our motivation is automatic optical inspection for printed circuit boards. We know that quality control is a very important task, and most of the electronic equipment has printed circuit boards inside it. Here we have an example of a short circuit. There is a critical defect. Recently, the DeepPCB dataset was published. It has 1,500 of image pairs. Together with this dataset was published a model to detect the defects using a referential approach. The referential approach works with a template image. There is a perfect PCB image and the defective PCB. Those images must be perfectly aligned, and there are some difficulties with misalignment and illumination difference between the template and the test image. This dataset, the DeepPCB dataset, has 6 types of defects shown here in this figure below: open, short, mouse bite, spur, Cooper, and pinhole. Our proposed approach is to evaluate transfer learning to classify DeepPCB dataset in a binary and multilabel classification using the non-referential approach. That means that we are going to show to the classifier a single image defective or not. In binary classification, we are going to classify regarding if the PCB has a defect or not. And in the multilabel classifier, we are going to classify for each type of defect, since PCB can have multiple defects on it. We are going to use this transfer learning strategy from VGG16, removing the final layers, the full connected layers from the output, and replacing it by new ones. For the binary classification, we are going to evaluate 2 input image size, the standard VGG16 input image size, and the DeepPCB dataset resolution, further referred as full image size. In a previous work, we found out that shallower models presented better accuracy in binary classification in this particular dataset. So we are going to also evaluate if the classifier layers were connected after block 5, as the figure below. And also, we are going to evaluate the results when the classifier layers is attached after the block 4. We are removing convolutional block 5 from VGG16. Regarding multilabel classification, we are going to have 6 output units. Each output works as a multiple binary classifier for each type of defect. Our methods, we used a multilayer perceptron classifier. We also used online image data augmentation with zooming, rotation, shifting, horizontal and vertical flip. Those are our results. The best model achieved 99.5% accuracy with all convolutional blocks from VGG16 and the full image input size. This is an interesting result because previously, reducing the input image size, the accuracy was 83.6%, and just increasing the input image size, there is a jump to 99.5% accuracy. Those are the misclassified images. Basically, we misclassified text in the PCB as a defect, and we didn't catch these types of defects in the border of the images, and also with these high complexity images, PCBs, that are very hard even for human. In the multilabel scenario, we achieved an average precision of 95.2%. Here in this table we have the accuracy and FUN score for each class. As a conclusion, the input image size is an important factor since the full image achieved an accuracy of 99.5%. It's worth mentioning that increase the input image size also increase the number of parameters. Regarding the multilabel classification, our model achieved neighboring results to the ones presented by Tang et al. With a referential approach. But the non-referential approach requires less information because only a single image is passed to the classifier. The non-referential could be a first step in an automatic inspection. Thank you for your attention.